Welcome to Spring LIB.
Hi everyone, so what we have here is a problem with a particle that has a mass of 0.5 kilograms and that's moving along a horizontal slot with the rotation of an arm. That arm is rotating at 2 radians per second and the path is defined as 0.5 secant theta. What we're asked to solve for is the force on the rod, or force from the rod on the particle, and also the force from the slot, the normal force, when theta is equal to 30 degrees. How we're going to do this is we're going to apply our knowledge of rotational motion in the r and theta direction and couple that with free body diagrams with Newton's second law in the r and theta direction to develop equations of motion and solve for these forces. So let's go ahead and get started. We know that r is equal to 0.5 secant theta. Therefore, r dot is equal to 0.5 secant theta tan theta times theta dot. And then we know that r double dot is equal to 0.5 times a quantity secant theta tangent theta squared times theta dot squared plus secant cubed theta times theta dot squared plus secant theta tan theta times theta dot. Now, when we know that theta is equal to 30 degrees, theta dot is 2 radians per second, and theta double dot is 0, we can solve for r dot, and r double dot using those equations we just solved, and we see that r is equal to 0.5774 meters. R dot is equal to 0.67 meters per second, and r double dot is equal to 3.85 meters per second squared. We can use these quantities to plug in for our radial and theta accelerations. So we'll see that AR, which is equal to r double dot minus r theta dot squared, is equal to 1.54 meters per second squared, and a theta is equal to r theta double dot plus 2r dot theta dot, which is equal to 2.67 meters per second squared. Now let's go ahead and draw our free body diagram. So here's our ball, or here's our mass. Here is the r direction, here's the theta direction. Here's the normal force, and here is F that is coming from the arm. And this angle right here is our theta of equal to 30 degrees. So by resolving these forces in the r and theta directions, we see that the net force in r, which is equal to m times ar, we can resolve these forces and say that n cos 30 minus mg cosine 30 is equal to m ar. And solving for n gives us that n is equal to 5.79 newtons. Next, what we can do is we can solve for F. And by doing that, we can say the net force in theta is equal to m times a theta. And we see that F plus mg sine theta, or sine 30, minus n sine 30 is equal to m a theta. Now we solved for n previously, so we can solve directly for F. And we see that F is equal to 1.78 newtons. So that is one part of our answer, and this is the other part of our answer.